Good day, I'm Norman Wapper. Today we're going to have a look at one of the many remarkable contributions made to number theory by the great Carl Friedrich Gauss, a champion of mathematics who lived from 1777 to 1855, sometimes called the Prince of Mathematics, and certainly one of the greatest mathematicians of modern times. He almost single-handedly reconfigured number theory at a tender age of 21 by this monumental book called Disquisitiones Arithmeticae, which gave all kinds of new directions for the subject. And part of that reconfiguration was this introduction of modular arithmetic that we're going to learn about today, which is a very useful and a valuable tool to understand divisibility, which has many modern applications to modern cryptography, for example, and internet security. Okay, so modular arithmetic is a technology for studying the arithmetic of remainders with respect to a fixed number m called the modulus. So basically we're looking at numbers from the point of view of one particular number m and basically concentrating on the remainders that other numbers make with respect to that fixed modulus m. So if we divide a natural number n by this fixed modulus m, then we're going to get a remainder r. And that remainder r can be any number from 0 up to m. It can include 0, but that's a special case when m actually divides n. But it can't quite be m, because if the remainder was m or bigger, then we could subtract another m from it, so it wouldn't be the smallest remainder. So this remainder r is something that we give a special name to, so we say that n mod m is r. That's what this terminology means. It's telling us what the remainder is when we divide n by m. So to motivate this, let's return to this question of whether 13 divides z or not. Z is 10 triangle 10 plus 23. So another way of saying that is, what is the remainder when you do divide z by 13? Here is z, this tower of 10 10s stacked on top of each other plus 23. And we should be aware that this question already is a little bit shaky because it's assuming that we have extended our arithmetic up to this very lofty level where z lives. Okay, that's already a little bit problematic. So we're working in some kind of num expression world, but we haven't actually been very precise about what that actually means. So let's put that kind of problem aside and let's just play around. So let's investigate this question, as you might have done, by just looking at powers of 10, very simple, modest powers of 10, in terms of what are their remainders when you divide them by 13. So it's a very profitable kind of investigation. So if we take 10 mod 13, well, that's 10. That's telling us that if we divide 10 by 13, the remainder is 10. How about 10 squared mod 13? Now it's a question of dividing 100 by 13. And over here I've done that. So 100 divided by 13, well, we can take 7 of them. 7 13ths is 91. And that'll give us a remainder of 9. Telling us that 10 squared mod 13 is 9. That's the remainder that you get when you divide 10 squared by 13. And then you can check that 10 cubed mod 13 is 12. And you might like to stop the video and, as a little exercise, first of all check this one here and see if you can see the pattern. How does this continue if we keep on going? Increasing the powers of 10 and always asking what is the remainder when we divide this bigger and bigger power of 10 by, say, 13. So we're fixing 13, that's our modulus m. We're interested in what are the remainders when we divide higher and higher powers of 10 by that modulus. It's a good question, well worth exploring. All right, let me remind you of some notation when we divide one number by the other. If we divide 100 by 13, as we've just done, then we get a quotient of 7. So 13 goes into 100 7 times. And then there's a remainder of 9. And we say that the 13, the thing that we're dividing by, is called the divisor. So there's the divisor, there's the quotient, and there's the remainder. So this expresses completely that arithmetical operation of long division that we've done. Okay, so suppose that we want to do the same thing for 1,000. We want to see what happens when you divide 1,000 by 13. So we could again do a long division. Okay, but something else that we could do is we could take the equation that we've just got and multiply it by 10. This is maybe a little bit clever. Okay, so we multiply this equation by 10. What do we get? We get 1,000 equals 70 times 13. We'll write it that way, plus 90. Okay, that's good because that's a multiple of 13. So now we're faced with the simpler problem of expressing 90 as a bunch of multiples of 13. It's actually 6 times 13, that's 78, plus a remainder of 12. And so now if we put these two together, we get that it's equal to 76 times 13 plus 12. So we've managed to get this without actually doing the long division. That's a good idea. So let's go up one step. If we go up one step to the next power of 10, we're going to just multiply this one by 10, and we'll get 10,000 is 760 times 13 plus 120. And again, what we're going to do is we're going to express this as some multiple of 13. Okay, this is some multiple of 13. I could write 760, but let me just write down question mark, meaning that there's something there, but I don't really care what it is. Okay? And I'm going to express the 120 as 9 times 13, which is 117, plus a remainder of 3. And then I'm going to write this as something times 13 plus 3. So however many 13s I had here, I'm adding it to a certain number of other 13s over here. I'm getting a certain multiple of 13s, and I'm not going to pay much attention to what that multiple actually is, because the only thing I'm really interested in is this plus 3, the remainder. This is sort of the idea of modular arithmetic, that we start focusing on the remainder and start actually ignoring the quotient. We know that there's some number there, but the point is we don't really care that much what it is. Because if we go to the next step and multiply by 10 again, then the effect is that over here we're going to get 100,000. And this thing here is a multiple of 13. When we multiply that by 10, that's going to be some other multiple of 13. But we don't actually need to calculate what that multiple is. We do have to calculate this. This is going to turn into 30 when we multiply it by 10. And then that 30 is going to be expressed as 26, which is 2 times 13 plus 4. And the 2 times 13 can be lumped together with however many 13s we had here to get some new unknown multiple of 13 with a remainder of 4. So we're kind of cheating here in a way that we're sort of forgetting or ignoring part of these equations. Right? So Gauss realized that it's possible to do this, that when we're working our way through these powers of 10, say, and looking at the remainders, we can very easily get away with just not knowing what these various quotients are at each stage. So what we've just established in the last slide is that 10 to the 5th is some unknown multiple of 13 plus 4. Let's carry on in the same direction. If we multiply this equation by 10, we get 10 to the 6th is some other multiple of 13 plus 40. The 14 can be written as, we divide it by 13 in our minds, it's 3 times 13, which is 39, plus 1. And then the 3 times 13 can be combined with this number of 13s for another unknown number of 13s. And we should note that this question mark that's appearing here does not necessarily represent the same unknown number as this question mark represents. So the question mark just means some unknown quantity for us right now. The point is that it's some multiple of 13 plus 1. When we multiply then by 10, we get that 10 to the 7 is some multiple of 13 plus 10. And then when we multiply by 10 again, the 10 becomes 100, which can then be written as 91 plus 9, and we get a 9. because the 91 is 7 times 13, so it meets up with these ones here. At the next stage, we have to multiply the 9 by 10, we get 90. And then we saw that we could peel 6 times 13 away from 90, that's 78, leaving a remainder of 12. And in fact, the pattern repeats what we've gotten previously repeats. The 12 becomes 120, which is 117 times 3, so we can peel off the 9 times 13s. And then we multiply by 10, we get a 30 again, which gives us a 4. We multiply by 10, we get 40, which gives us a 1. So the pattern is repeating. You can see it right here. It's 1 remainder, then 10, and then 9, and then 12, and then 3, and then 4, and then 1. And then we're back exactly to this situation. Right? This thing here looks exactly like this thing does, except that the multiples might be different, but we don't care about the multiples, so the essential form is the same. This is really the motivating kind of, or a motivating reason for establishing this modular kind of notation. Okay, so now that we have a pattern of the remainders for powers of 10, let me give you this exercise again to see if you can then get a little bit closer to finding Z mod 13. Can you jack this up now to finding out what exactly this remainder is? All right, so now let's set up this modular arithmetic. We're going to start with a fixed natural number m, and that's called the modulus. And we'll want that number to be bigger than or equal to 1. Now these other numbers, k, l, and n that we're going to be talking about, they're all from natural numbers. So that's sort of the default realm that we're talking about. So the definition is this, that k equals l, but it's a funny equal sign with 3 bars, not 2. And we read it by saying k is congruent to l mod m, but it's a kind of equality. Now this means the following. It means that k mod m equals l mod m. And I remind you, that means that the remainder that you get when you divide k by m equals the remainder that you get when you divide l by m. So in other words, k and l have the same remainder when divided by m. That's what k congruent to l mod m means. So for example, 100 is congruent to 10 to the 8 mod 13 because both of them have a remainder of 9 when divided by 13. We saw that 100 mod 13 was 9, and 10 to the 8 mod 13 is 9. So 100 and 10 to the 8 have the same remainder when you divide them by 13, namely 9. And so we say that these two are congruent mod 13. Congruent mod 13, that's what we say, to denote this modular kind of equality. So here's another example. So here's some numbers which are all congruent mod 7. So we're changing our modulus now from 13 to 7. Okay, so we're looking at numbers mod 7. That means we're only really interested in the remainders when you divide by 7. So when we're looking mod 7, we only care about what's the remainder when we divide by 7. So the remainder of 10 when we divide by 7 is 3. The remainder of 3 when we divide by 7 is 3. The remainder of 17 and of 24 and of 31 when we divide by 7 are all 3. So all of these numbers are congruent mod 7. And notice that, say, these two are differing by, well, 7 in this case, and these differ by 14, which is a multiple of 7. These differ by 7, these differ by 14. Here's another example. It doesn't have to be a prime, so mod 6. If we're working mod 6, we're interested in the remainders that you get when you divide by 6. In that case, 0 is congruent to 6, because 6 is divisible by 6. The remainder is 0. 12, if you divide that by 6, you also get a remainder of 0. 18, when you divide by 6, you get a remainder of 0. 24 also. So the things that are congruent to 0 mod 6 look like they're just the multiples of 6. Here's another example, maybe a kind of trivial example, when we're considering mod 1. So we did allow our modulus to be 1. So what happens if we're working mod 1? Well, in that case, every number is divisible by 1. The remainder when you divide 4 by 1 is 0. So all numbers are congruent to 0 mod 1. That means they all leave a remainder of 0 when divided by 1. And here's another example. 334170 is congruent to 334178 mod 8. How do we know that? Well, because this number and this number only differ by 8. Okay? So actually I don't know what the remainder is when I divide this by 8. But I do know that the remainder that I get when I divide this by 8 is going to be the same as the remainder that I get when I divide this by 8, because these two only differ by 8. So they're congruent mod 8. Now here's another way of thinking about this fundamental definition of things being congruent mod m. So let's say m, k, and l are all natural numbers, and let's suppose for the convenience that k is less than or equal to l. All right. Then k is congruent to l mod m is precisely the same as m dividing l minus k. If the difference between k and l, this l minus k, is divisible by m, then these things are congruent. And conversely, if these two things are congruent, then their difference is divided by m. And why do I insist that k is less than or equal to l here? Well, it's just so that we're still working in the realm of natural numbers. I haven't really defined things for integers yet. In fact, strictly speaking, this is really independent of having an arithmetic for integers. Okay? It's just a natural number arithmetic. That's all what we need here. So I just want to be a little bit careful when you're subtracting with natural numbers. You have to be careful that you don't go outside the bounds of natural numbers, and we make sure of that by just requiring that this number be bigger than or equal to this number in order that this thing is still a natural number. And that's a little bit of a subtlety that appears in the proof here. It's a little bit of an artificial subtlety, but it's okay. So here's the proof. So suppose that, say, k is some multiple of m, say n1 times m, plus a remainder of r1. So this is really the remainder, so that the remainder is between 0 and m, not equal to m. And similarly, L, say, is n2 times m, plus the remainder r2, r2 also having the same form, less than m. Okay, so what does it mean for k to be congruent to L mod m? It simply means that these two remainders are equal. So this happens precisely when the remainders r1 and r2 are equal. That's our previous definition of what this means. Okay, on the other hand, if we look at L minus k over here, so the L minus k over here, well, it's this number, minus this number. Okay, so when is this going to be divisible by m? Well, here's a multiple of m, and here's a multiple of m, and here we have r1 minus r2 sort of left over. So this is going to be divisible by m precisely when r1 equals r2, because r1 and r2 are less than m. So there's no way that a difference between them can be a multiple of m unless that multiple is 0. So as an exercise, please check this claim. Just go through the argument. Actually, strictly speaking, you have to look at a couple of different cases depending on the relative sizes of r1 and r2, because we don't know whether r1 is bigger than r2 or the other way around at this point here. Okay, so the moral of the story is that these two notions of congruence are really the same. We can say that k is congruent to L mod m means that the remainders, when you divide by m, are equal. Or another way of saying it, equally valid way of thinking about it, is that the difference between these two numbers is divisible by m. And sometimes this is taken to be the definition of what this means. That's perfectly valid. Now, if this was a course in number theory, I would probably have to go a little bit slower. And in particular, especially with this theorem here, which is a core result in the subject, we'd have to have a close look at the proof. I'm not going to go through the proof, but they are great exercises for you to try to prove these various things. So the setup is that we have a bunch of natural numbers, say k1 and k2, and L1 and L2, and m, which will be our modulus. M is going to be bigger than or equal to 1. Maybe I didn't say that. Let's assume m is bigger than or equal to 1. Okay, let's suppose that k1 is congruent to L1 mod m, and that k2 is congruent to L2 mod m. That's our starting point. Then, the sum k1 plus k2 is congruent to L1 plus L2 mod m. And the product k1 times k2 is congruent to L1 times L2 mod m. Now, actually, these are lovely little exercises that you can use using that last proposition. It's a very nice way of proving it. So, for example, let's have a look at m being 13. Our modulus is m equals 13. Then 100 is congruent to 9 mod 13. We've seen that. And we also calculated that 1,000 is congruent to 12 mod 13. So according to this theorem, that means that if we take 100 and we add it to 1,000, so giving us 1,100, then that's going to be congruent to the sum of 9 and 12, which is 21. Now 21 is congruent to 8, because if you subtract a multiple of 13, you get 8. And so we see that 1,100 can be said to be congruent to 8 mod 13. On the other hand, if we multiply these two numbers, we'd get 100,000 on the left, and that should be then congruent to the product of 9 times 12, which is 108. And we can sort of simplify that mod 13 by taking multiples of 13 out of here. So 104 is 8 times this. So if we take 8 times 13 out, that's 104 out, then this 108 becomes 4. So 108 is congruent to 4. That means that 100,000 is congruent to 4 mod 13. And you can check that's the result that we got earlier. Okay, so a related theorem to the one we just proven, in fact a consequence of it, is this very pleasant thing here, that if k is congruent to L mod m, then k to the n is congruent to L to the n mod m for any natural number n. You can see, I hope, that that's sort of a consequence of the previous one, because we apply that multiplicative property to the equations k is congruent to L mod m, and the same equation k is congruent to L mod m. We just multiply those two, then we get k squared is congruent to L squared. And then if we multiply by the same equation, we get k cubed is congruent to L cubed, and so on. Okay, so a pleasant exercise to prove these, both of these theorems. So let's illustrate this one here. So 100 is congruent to 9 mod 13. We've had that several times. So applying this, say, to n equals 2, would tell us that 100 squared is congruent to 9 squared, or 81. But 81 is congruent to 3 because we can take out 78, which is 6 times 13. And so we get 100 squared is congruent to 3. We could take this equation and apply the same kind of reasoning. We could square both sides. 100 squared is 100 to the 4th. 3 squared is just 9. So we get very quickly that 100 to the 4th is congruent to 9 mod 13. And if we square this one again, then we get that 100 to the 8th is the same as 9 squared, which is 81, which we've already seen is congruent to 3 mod 13. So you can see that by using these theorems, we can very quickly prove things that otherwise would require quite a few steps to get up to. Now, this is a very efficient way of deducing this relatively high power of 100. What its remainder is mod 13. Its remainder, when you divide 100 to the 8th by 13, the remainder is 3. And say if we square this again, we'd get 100 to the 16 is congruent to 9 mod 13. It's very pleasant. The genius of Gauss to realize that we can exploit the separation of quotients with remainders in this very pleasant and natural but clever way. Okay, but the subject actually has ties. This is a language to talking about divisibility, but that subject has been around for a lot longer than Gauss. So even back in the earlier days in the 16th, 17th, and 18th centuries, we had Fermat and then Euler coming up with very important results that are pleasantly stated in this language, but actually predated. And so that's what we're going to look at in our next video. We're going to look at two famous theorems of Fermat and Euler, which address this kind of issue of what happens to powers of a number when you look at it from the point of view of a fixed modulus. What happens to powers of 10, mod 13, say, as the power keeps on going higher and higher and higher? Turns out that there's a very pleasant pattern that depends, well, on the number that you've chosen to take powers of, but also on the modulus in an interesting way. We'll discuss that. It's a topic that has lots of applications to modern internet security, actually. Hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.